The math for chapter 2 is pretty straightforward. There's a couple equations we have to look at. First of all, the average speed of an object is the total distance traveled over the total time. It's important that we understand this is the average speed. So if you took a trip from Yuba City to Sacramento and it took you 45 minutes, you take the distance from here to Sacramento and divide it by the 45 minutes. However, that would not tell you how fast you were going at any given point in time. That just tells you your average speed. This equation can be solved for any of the variables. We can solve it for distance, or we could solve it for time. But it's still the same equation. The other equation we use is the definition of acceleration. Acceleration is defined as the change in velocity over time. That delta sign, that means change. Anytime you see a delta in physics, it means change. And mathematically, when we do a change, we take the final quantity and subtract the initial quantity. So for instance, delta V, delta speed, means that the final speed minus the initial speed is our change in speed. Okay, never initial minus final, always final minus initial. We can use that equation as is, but we could also substitute in what we just wrote and make it look more like this. It's a little bit more usable like this. Many of the problems you're going to do are going to start off from rest. When you say the word rest, you mean that the initial speed, or the final speed, if you come to rest, so let's get rid of that, is 0. Now, if I manipulate this, I can multiply both sides by t, and I get that v final minus v initial equals a times t, and then if I add the initial speed to the other side, I get something like this. If you know 3 of these things, you can solve for the 4th. Let's just do a quick example to see what I'm talking about. We'll do an example of each. Alright, I have a problem where we have a dragster, not that great, better than nothing. We have a dragster that's going to start off at 15 meters per second and speed up to 25 meters per second, and it's going to do it in 4 seconds. Now when I approach a problem like this, the first thing I do is assign variables to these numbers. It starts at 15 meters per second. Meters per second means it's a speed, so I'm going to call this the initial speed. It ends up at 25 meters per second, which again is also a speed, so I'm going to call that the final speed. And then seconds means it's time. And the question said, what's the acceleration? Okay, well, acceleration is defined as the change in speed over the time. So the change in speed, remember we said before, is final minus initial, and divided by the time it takes to do that. If you notice, this equation is already solved for acceleration, so we just have to plug the numbers in. So I'm going to take 25 meters per second, subtract 15 meters per second, divide that by 4 seconds, which gives me 10 meters per second over 4 seconds, which is 2.5 meters per second squared. And yes, the units for an acceleration is meters per second squared. Technically, it's meters per second, but it works out to be meters per second squared. Another example might be, if I have a car that can drive at a speed of 50 meters per second, and it travels a distance of 300 meters, how long is that going to take? So what I'm looking for is the time. What I know is the speed, the average speed of it, and I also know the distance we're traveling. So looking at this, I see that I've got speed, distance, and time, and so this equation seems like the most likely one to get me where I want to be. I'm solving it for time, so I'm going to multiply both sides by t, and then divide both sides by v. And I'm going to get that time equals distance over speed, so that's 300 meters at 50 meters per second equals 6 seconds. Pretty straightforward stuff, and the problems in your book you're going to find to be pretty much a piece of cake.